and welcome to this course on gas turbines and jet engines. So, today is lecture number 40, which is the final lecture of week 8. Okay. So, today we are going to analyze turbojet engine with afterburners. We have seen what is an afterburner, how it augments the thrust, so when is it necessary. Okay. So, today we will see how to quantitatively analyze the functioning of an afterburner when it is attached to a or when it is part of a turbojet engine. So, the concept that we will be cover is methodology. We will learn the methodology of solving numerical problems on turbojets with afterburner. Okay. So, the main difference here is that the presence of afterburners. So, we will take up the same problem as previously discussed, because then we can see and compare the results of the use of afterburner without the use of afterburner. Okay. So, if you remember in the previous problem which we had taken, we had the following design parameters. We had flight altitude of 10,000 meter, at which the ambient pressure was 0.265 bar and ambient temperature was 223.3 Kelvin. Then cruise speed was given, means the flight speed Mach number was 0.8, compressor pressure ratio was 8, then the maximum temperature or the turbine inlet temperature was 1200 Kelvin. Then all the component efficiencies were given, isentropic efficiencies. There was 4% pressure loss in the combustion chamber and the calorific value was also given. We needed to find the specific thrust and thrust specific fuel consumption. So, we proceeded step by step. We first did the calculation for diffuser, then compressor, then combustion chamber, then finally turbine and nozzle, and found that the specific thrust is 612.5 Newton per kg per second and the thrust specific fuel consumption is 0.1278 kg per Newton per hour, okay, or kg per hour per Newton. So, now we want to take the same framework, but want to consider a situation where a afterburner is also present in the same turbojet and now the afterburner is switched on. Okay. Certain additional parameter values are also given, design parameters for the afterburner, so that we can do the performance calculations. So, what are these additional parameters? It is stated that for the afterburner, okay, so T max with afterburner is 2000 Kelvin. Okay, we can go to very high temperature. So, previously we were limited by the turbine blade material. Now, after the turbine in the afterburner section, we know that we can go to very high temperature. So, we have taken 2000 Kelvin. Okay. And the combustion efficiency for the afterburning process is given as 0.98. Okay. So, now we need to find for the same conditions as previous, what is the specific thrust and what is the thrust specific fuel consumption. The same two things we need to find, but now with the afterburner running. So, remember what is the exit condition from the turbine. The turbine exit condition previously was given as, let us use another color. So, 996 means we derive that this is equal to 996.69 Kelvin. So, from this 996.69 Kelvin, the afterburner takes the conversion products to 2000 Kelvin and then it is expanded in a nozzle. Okay. So, if we draw the schematic quickly, just for reference. So, we know that we will draw something like this, which we had done in the previous class also. So, there is the diffuser, then the compressor shown here using a convergent section, then the divergent section shows the turbine, in between we have the combustion chamber, Of course, it is around the periphery, but for schematic we are just drawing one combustion chamber. And then we have the afterburner section after the turbine. This represents fuel injection in the nozzle. This additional length of the duct is present for sufficient to allow for sufficient time for the afterburning process. Okay. So, this is state A outside, state A outside. Then after the diffuser we had state 1, after the compressor we have state 2. Okay. Stagnation states are 0 1 and 0 2, this is the compressor. After combustion before the turbine we have state 0 3. After the expansion in the turbine we have state 0 4. Now, we have the afterburning process. So, after afterburning process or the second heat addition we have state 0 5, and at the exit of the nozzle the static state is 6, stagnation state is 0 6, but our important parameter here is the static temperature. Okay. So, this is our schematic diagram, and based on this in the previous class without the afterburner we had drawn the TS diagram. So, we will use the same TS diagram, this is from the previous class. So, we had process going from 0 A to 0 1, okay. This was the diffuser process, 0 1 to 0 2, compression process in the compressor, then combustion chamber with some pressure loss, then the expansion in the turbine. Up to that will remain exactly same as in the previous case. Okay. So, but after this expansion in the turbine, when we are at state 0 4, then we will have again secondary combustion in the afterburner, and this will occur at constant pressure, means if we ignore the losses. So, no losses are given. So, we will assume constant pressure. So, the temperature increases here, right, temperature increases and goes to very high value around 2000 Kelvin, not around 2000 Kelvin, it is given that this is exactly 2000 Kelvin. So, this will be our state T 0 5. So, corresponding state after expansion in the nozzle, the corresponding state is, so we will draw with another color, is 6. Okay. And the ideal state means isentropic expansion state is 6s. So, what we can see here visually also from the diagram is that because the constant pressure lines are diverging, this is P 6 and let us say that this is P 0 5, the constant pressure lines are diverging. So, the amount of energy which is extracted and converted to kinetic energy when the afterburner is used is much larger as compared to the kinetic energy which is obtained in the nozzle without the afterburner. Okay, that we can see because the constant pressure lines are diverging, and that is the main reason we are using afterburner. The temperature will increase, and because of the increase in temperature the velocity also, exhaust velocity will increase, and we will have larger thrust, which the larger thrust will be generated. We will have to see what happens to the specific fuel consumption, thrust specific fuel consumption, but we have discussed that generally the efficiency gets reduced. So, thrust specific fuel consumption increases. Okay. So, these are not used for efficiency, these are used for augmenting the thrust when required. So, now let us continue our calculation. So, at the exit of the turbine we had derived all the parameters values, so and those will remain same because there is no change up to this point, right. So, T 0 4 and P 0 4 are known to us. If this is an independent problem, we would have started with the diffuser, calculated for the diffuser, compressor, combustion chamber, turbine, and then we would have reached this point. Okay. So, T 0 4 from here we know that it is 996.69 Kelvin. 996.69 Kelvin, and P04 we have also calculated 1.309 bar. Considering the isentropic efficiency, this was derived 1.309 bar. This is Kelvin. Now, what is the next step? We already know that. So, now we will do the calculation for the afterburner. First, we want to find out how much is the additional mass flow rate, okay, because now we are adding fuel again. So, there is some additional mass flow rate, we want to calculate that. Okay, so, we will do an energy balance in the afterburner. Energy balance. So, what is the final energy of the fluid after the afterburning process? We are at temperature T05. Okay. So, the total amount of mass flow rate there is 1 plus F is the original fuel air ratio, and let us say that F2 is the additional fuel air ratio. So, additional fuel addition. So, fuel air ratio due to additional fuel addition, 1 plus F2 CPG T05. This is the final value of the means final energy of the combustion products multiplied by m dot A minus m dot A. What is the energy at the inlet? So, at the inlet the mass flow rate is m dot A 1 plus F. Okay. Still remember 1 plus F is there, and the specific heat also here is CPG, not CPA, because these are already the combustion products, and we are assuming that although the composition changes, the combustion products have the same Cp as an approximation for simplifying the calculation. Otherwise, it becomes very complicated, the calculation. So, CPG T04, this should be equal to the energy which is added from the chemical energy of the fuel. So, the mass flow rate of fuel addition is m dot A into F2, this multiplied by the combustion efficiency of the afterburner multiplied by the calorific value of the fuel. Okay. So, this is our energy balance. So, from here we should be able to get F2, everything else should be known to us. So, F2 comes out to be equal to, so mass flow rate gets cancelled. So, F2 comes out to be equal to, so the expression is CPG T05 okay, minus CPG T04 whole thing multiplied by 1 plus F. So, we are taking all the F2 terms to one side and all the other terms to the other side. This divided by eta B2 calorific value QCV minus Cp of gas T05. You can rearrange the terms and you will get this expression. Okay. So, now what are the known values? Cp of gas 1.148 kilojoule per kg Kelvin, T05 2000 Kelvin, again Cp of gas is known, T04 is known to us, T04 is where did we write 996.69 Kelvin, 1 plus F. So, F is also known to us from previous calculation. We had found that the value of F is 0.02174. 0.02174. Okay. Eta B2 is given 0.98. Calorific value of the fuel is known to us. It was given as 43,100 kilojoule per kg. Okay, let us verify that 43,100 kilojoule per kg. Then CPG T05 already known to us. So, when we substitute all the values, we get that the second fuel air ratio is 0.02946. Okay. You should do the calculation on your own and verify that you are also getting the same amount of fuel air ratio. Okay. So, this is fuel air ratio, right, not air fuel ratio. So, after this now we can proceed with the calculation of the second nozzle. Okay. We now know the pressure at the inlet and temperature at the inlet of the afterburner, pressure and temperature at the exit of the afterburner. Temperature at the exit of the afterburner T05 is given as 2000 Kelvin and pressure at the exit of the afterburner P05 without assuming or assuming that there are no losses, this comes out to be equal to P04, which is 1.309 bar. Okay. So, now let us go to the calculation of the nozzle. Okay. We will do at the side here, because we can then easily refer to the diagram. So, now for the nozzle, what do we know? We know that T05 is 2000 Kelvin, which is the entry point of the nozzle. Now, let us assume that the nozzle is choked. Okay. Assume that the nozzle is choked. Then we will see what are the critical values. So, in that case, T star equal to T6, okay, and T06 by T6. So, this is T06, T06 by T6 is equal to T05 by T6 or the other way around. Okay. So, we are relating the stagnation and static values T06 by T6, but because T06 is equal to T05, because there cannot be any change in enthalpy in the nozzle. So, we can write this as T05 by T6 and then we know that T05 is 2000 Kelvin and T6 is unknown. So, this should be equal to, at choked condition, this should be equal to gamma g plus 1 by 2, where gamma g is 1.333, right. So, using this now we find that T6 is equal to 1714.53 Kelvin, okay. Very high value if you compare with the previous case where T6 came out to be, means in that case it was denoted as T5. So, it was 854, now we have a very high value 1714.53 because of the afterburner. So, now what is the next step? We have to see whether the nozzle is choked or not. Okay. To do that, we have to find the point T6s, okay, the temperature T6s at 0.6s, then the pressure, and then from the pressure ratio we can see whether we are at a higher pressure at 0.6 compared to atmospheric pressure, or we are at a, means the critical pressure is lower than that. If it is lower than that, then our exit condition will be atmospheric pressure. So, that is our next step. So, we will continue this. This is the afterburning process. So, we are drawing again the afterburner process and the nozzle expansion. This is 0.05, this is 6, this is 6s, this is 0.6. Okay. So, we have found what is the value of T6. Now, next step is to find the value of T6s. So, for this we will use the nozzle efficiency, we are assuming same nozzle efficiency. So, eta n equal to actual change in enthalpy T05 minus T6 by the ideal change in enthalpy T05 minus T6s. Okay, we have cancelled the Cp, so we are writing in terms of temperature T05 minus T6s. Actually, this is the ratio of the enthalpy difference H05 minus H6 divided by H05 minus H6s. Now, if we assume the Cp to be constant, we can cancel the Cp from the numerator and the denominator. So, eta n is given as 0.95, right. Let us verify this quickly. So, eta n is given as 0.95. This is equal to 2000 minus 1714.53 by 2000 minus T6s, okay, from the equation of the isentropic efficiency of the nozzle. So, now T6s can be obtained and T6s comes out to be equal to 1699.5 Kelvin. We expect this to be lower than the T. So, T6s should be lower than T6 value, because more expansion will happen in ideal case, and that is what we are finding, that this is lower than, slightly lower than the value of T6. So, once we have T6, we can calculate the pressure P6 using the isentropic relation between 0.5 and 6s. Okay, so, this will be between 0.5 and 6s. So, P05 by, so at 6s also the pressure is equal to P6. So, P05 by P6 is T05 by T6s whole to the power gamma of the gas gamma g by gamma g minus 1, where this gamma g we know that this is 1.333. P6 is unknown, P05 is known to us, we have already seen that P05 equal to P04 is equal to 1.309 bar, and T05 and T6s are also known to us. So, finally, we get P6 from here to be equal to 0.682 bar. How does it compare with PA? PA is given as 0.265 bar, okay. PA is given as 0.265 bar. So, our critical pressure is significantly higher than that. So, as P6 is greater than PA, P6 is the critical pressure, right, because we have assumed that the nozzle is getting choked. As P6 is greater than PA, our assumption of choked nozzle is correct. So, our assumption of choked nozzle is correct. Okay. So, now what do we want to do? We first will find the velocity. So, because the nozzle is choked, V6 is equal to C6, which is equal to gamma of the gas 1.333 multiplied by R multiplied by T6. Okay. T6 is also known to us. So, this comes out to be equal to 809.89 meter per second. So, this should be significantly higher than the case without running the afterburner. So, without the afterburner, our velocity was 571.733. Okay. Now, in the present case with the afterburner, it has increased to 809.89. So, you can clearly see the role of the afterburner. Now, we also have to find the pressure thrust, because the pressure difference also will create a lot of thrust. There is a significant pressure difference. Will the pressure thrust remain same? It will not remain same, because the area will have to change to accommodate for the additional volume flow rate. Okay. So, let us see what is the pressure thrust. So, for that first we find what is rho 6. Rho 6 is P 6 by R T 6. P 6 is known to us 0.682, just now we have calculated, into 10 to the power 5, by R is 287, and T 6 also we have calculated, T 6 is equal to 1714.53. So, from this now we find that the value of rho 6 is equal to 0.1386 kg per meter cube. How does this compare with the previous case without afterburner? So, without afterburner the density was 0.2782. So, it has become significantly lower because of the high temperature, it is almost half of the previous case, which means that for the same mass flow rate now we will need larger volume flow rate. So, we will need larger cross sectional area of the nozzle exit, okay, because nothing means everything else remains constant. So, therefore, our area A 6 is equal to mass flow rate m dot A. Now, what is the mass flow rate, actual mass flow rate? M dot A 1 plus F plus F 2, because we have additional mass flow rate due to the second fuel addition, okay, second fuel injection. This divided by rho 6 V 6. Okay. So, rho A V is equal to m dot. So, A is equal to m dot by rho V. So, everything again is known here, 1 plus F 2 divided by rho 6 V 6, everything is known, only m dot A is not known. So, our result will come in terms of m dot A, which is 9.3647 into 10 to the power minus 3 m dot A. Okay, so, then we will add another slide. So, this is our value of m dot A, means A 6 in terms of m dot A. Now, we can find the specific thrust. So, the specific thrust in this case is the sum of the specific thrust due to momentum thrust and due to pressure thrust. So, I is equal to F by m dot A. So, this F is equal to m dot A 1 plus F plus F 2. This is the mass flow rate, m dot A into 1 plus F plus F 2 in the nozzle, V 6 minus m dot A into V A. Okay. So, this is the momentum thrust plus the pressure thrust is P 6 minus P A multiplied by A 6. Okay. This divided by the mass flow rate of air should give us the specific thrust, okay, or impulse. So, m dot A will get cancelled in the P 6 minus P A into A 6 equation also, A 6 is in terms of m dot A. So, ultimately all factors are known values. So, we will get the value here as 611.73 plus 390.5 Newton per kg per second, okay, Newton per kg per second, which is equal to 1002.24 Newton per kg per second. So, how does it compare with the previous case? If you go to the previous case, the momentum thrust was 344.5, now it has increased quite drastically to 611.73. What about the pressure thrust? Pressure thrust was 267.97. So, this has also increased now Now, this is equal to 390.5. Okay. Why this has increased? Because of the increase of area, not because of the pressure change. So, finally, the total specific thrust is 1002.24, which will be much higher than this value of 612, which we had obtained without afterburner. Same problem, you can consider that afterburner is switched off and the afterburner is switched on. So, finally, we can find the thrust specific fuel consumption TSFC. So, this TSFC is equal to, how do we calculate it? M dot F by F, okay, the mass flow rate per unit thrust. So, this is M dot A F by M dot A I, okay, F is the total F in this case. So, this is equal to F plus F2 by I. We know what are the values of F and F2. So, I comes out to be equal to point, okay, let us write in the SI units first, 5.109 into 10 to the power minus 5 kg per second, okay, mass flow rate per unit thrust per Newton. This can be converted to a more practical term by multiplying by 3600, 109 into 10 to the power minus 5 kg per hour mass flow rate per unit thrust Newton per Newton. So, this comes out to be equal to 0.184 kg per hour per Newton. So, we expect this to be higher, much higher than the case without the afterburner. We have discussed that the efficiency goes down. So, fuel consumption increases, even the specific fuel consumption also increases. Of course, the actual fuel consumption increases by a very large amount. So, previously we had the specific fuel consumption as 0.1278 or 0.128. Okay. So, previously we had the specific fuel consumption as 0.128. Now, it has increased to 0.184. So, it has increased quite significantly. Okay. So, you can see the effect of afterburner, switching on the afterburner on the thrust and on the specific fuel consumption. If the mass flow rate of air is given, we can find the actual thrust and actual fuel consumption also. So, you should try the same problem, but assume that, so I am just leaving this as an exercise for you. Assume that we have a CD nozzle instead of a conversion nozzle. Okay. In that case, what will be the expansion? Expansion will go until the pressure is equal to atmospheric pressure, because there we are not restricted to the choke pressure. We, in the divergent part, we can go to lower pressure. So, then in that case, what is the value of specific thrust and thrust specific fuel consumption, you should find out. So, what do we expect? So, I had discussed that in general, using the momentum or getting a momentum thrust instead of pressure thrust is more beneficial, because once you means in momentum thrust you will get more, basically more efficiency in terms of getting more thrust with the same amount of fuel. So, for this same case, we expect that the overall thrust should be little higher, because we are now converting the entire thrust to momentum thrust. So, the value comes out to be equal to 1019.77 Newton per kg per second. Please verify. So, this is slightly larger than the 1.002.24 Newton per kg per second, which we had obtained with the conversion nozzle. Okay. And so, not much difference is there. So, it means that conversion nozzle still is quite good, and it is much more practical to use, much more easy to design. So, if we go to even high values of pressure ratio, then convergent divergent nozzles will make more sense. So, the V6 in this case exhaust velocity would have been much higher because of the use of the CD nozzle. This comes out to be 1198.06 meter per second. Okay. This is going to be significantly higher as compared to the conversion nozzle, where the velocity is limited to the speed of sound. So, 809.89, now it is 1198.06 meter per second. One final point before we end the class today. So, what you can see in the case of conversion nozzle, that the choked velocity, the sonic velocity at choked condition is 809.89 meter per second. So, this means that at this temperature the speed of sound is very large, 809.89 meter per second. So, even if the aircraft is flying at Mach 2, the aircraft speed will be, if it is let us say Mach 2 instead of 0.8. So, the aircraft speed will be 2 times the speed of sound at ambient condition. So, at ambient condition the speed of sound was 299.54. So, now it would be 2 times into 299.54. So, around 600 meter per second, 599 meter per second. Okay. So, this will be not be MA, this will be VA. So, this will still be less than the exhaust gas velocity. So, the conversion nozzle is still sufficient, although it is limited to Mach 1, the aircraft velocity can go to Mach 2 also, because the speed of sound is different at different temperatures, and the exhaust gases are at a much higher temperature as compared to the ambient. Okay. So, I hope you have got a very good idea about the a very good idea about comparison between the afterburner case and without afterburner case. Please try similar problems given in the assignment set. Okay. So, with this we will conclude. We have analyzed turbojet engine with afterburner, and in the next class, from the next class onward, we will go to a next to another type of engine, which is very widely used nowadays. It is the most common type of engine used nowadays, which is known as turbofan engine. Both for military aircrafts it is used as well as civilian aircrafts, and mostly for almost all large civilian aircrafts turbofans are used nowadays. Okay. So, these are the references. Thank you.